In this laboratory, we are going to talk about DC motors and test a DC motor. Most DC motors that students typically see will look something like this. There's a motor, there's a gear head, and two wires, right? Typically red and black for DC. Here's another example of a motor system with just two wires. Now, these DC motors, these small DC motors, are what we call permanent magnet DC motors. That means inside the body of the motor, there is a permanent magnet. And with permanent magnet DC motors, often called PMDC motors, they only need two wires. Now, some of the motors we'll work with will have more wires, such as this one. But you'll notice the red and black wires are the power wires. The other four wires, green, brown, yellow, orange, are part of the encoder. So the position information. But so there's still just the two red and black wires, right? Even on this Maxon motor here, we see the blue wires are the part of the encoder. The actual connections to the motor, there's one copper wire there and one copper there. So that's still a two-wire motor. When we go to larger size motors, we have a little more complicated situation that we refer to as a shunt motor, and that is the unit we will test. It's just called a DC machine. The reason why we call it a DC machine is that it could actually be either a motor or a generator. So there are two sections to every DC motor. The first part is the rotating section we refer to as the rotor. And the rotor actually includes three components. The rotational part, which is the rotary winding, often called the armature winding. And then this section on the outside, referred to as the commutator, and then these two components here are called the brushes. But there's still just two connections to that rotating section of the motor. If we look inside the motor, we can actually see the components that we just referred to. The brushes are the carbon, the commutator is this copperish looking section, and then the winding is back inside of the motor. A little harder to see, but you'll see it in the lab. Because this is not a permanent magnet motor, we need a method for creating the extra magnetic field, which the permanent magnet provided. And we do that through a winding. Now, this motor has two windings, a shunt winding and a series winding. It also has a variable resistor or rheostat. For power resistors, we call them rheostats. Allows us to control the current in this shunt field. Now, the shunt field provides the magnetic field. Actually, you could use the series or shunt field, but we're going to use the shunt field. So let's take a look at the circuitry and the connections that we'll see on this motor. So here's our shunt motor. It has two circuits connected in parallel or shunt. The rotational part, the motor rotational circuit, which includes the rotor winding, the brushes, and then the commutator segment, which is not shown in this picture because it's all together. In parallel or in shunt with that is a motor winding, the shunt winding, and then the variable resistor or rheostat. And then out here is the applied DC voltage. So the permanent magnet motor does not need this because it is providing the magnetic field through a permanent magnet, not a current flowing in the winding. So we have a little more complicated wiring setup, which we'll look at now. Now, the wiring setup we will use, we have a DC power supply over here. This power supply is capable of 120 volts up to 8 amps, and that will supply the main voltage and current to the motor. The connections to the motor are very straightforward and follow the diagram we just looked at. Power red goes to this terminal, could be either terminal. It will change the direction depending on current flow, but that doesn't affect your circuit. This is the rotational part of the circuit, and then a black wire returns to the power supply. On the shunt winding, we come from power, a red wire, down to the shunt winding, and we're going to bypass variable resistor because we don't need it, at least not for the first part. So we have two circuits, one in parallel, one the rotational component and one the fixed component. Now, in order to test a motor, we also have to provide a load. So the load in this case is the electrodynamometer. So a dynamometer is a unit which takes mechanical energy and basically turns it into heat. But we do that using an AC power connection, which will connect to these two yellow terminals, and it is connected back here to the 120 volts. This control over here allows us to control the loading of the motor. So when we turn this knob, you'll hear the motor change in terms of speed and loading. And this the dynamometer will show you the torque. We'll have to measure the speed. As the dynamometer turns, you can read the torque value underneath the rotational part. This torque reading is in pound-force inches, and we'll have to convert if you get a motor with a Newton meter. When you look at a data sheet for a motor, most typically you will see a graph or a series of plots similar to this. This is fairly complicated graph because there's 1, 2, 3, 4 different graphed data and also a vertical line showing the rating point. But in reality, this is a much simpler graph when you take the data. The actual data that we need is simply the speed data, which is shown in the blue line, from no load speed to full load speed. We will not stall the motor. And then the input current. Now the horizontal axis here is torque. The vertical axis will be a dual axis, one with speed, one with current. So what we have is torque and speed. Torque and speed is power, mechanical power, which is the output of the motor. And then we have current. Now what these graphs don't often emphasize is that this is for a constant voltage system. So you would have, if this was a 24 volt motor, you'd have 24 volts for all operation, or 120 volts if we're using the motor we will in the lab. So current times voltage is also power. So voltage times current is input power, and then we have the input power and output power. Now once you have the input power and the output power, this graph makes a little more sense. The output power, which is the yellow curve here, is simply the motor torque times the motor speed. And it forms this typical parabolic type curve, inverse parabolic, because we start with no load or zero torque and all speed, which is of course zero power. And then over here at the stall point, we have zero speed and lots of torque, which is also zero power. So since the curve of the speed is simply a line, or typically nearly a line, from no load speed to zero, and the torque is also linear, then you'll get this inverted parabolic curve. Obviously, the top here is the max power output. Now, from that point, right, we can also get efficiency. Now, efficiency is power out over power in. And of course, power out is the mechanical power out, which is torque times speed, and the power in is the voltage times the current. And so now we have been able to deliver 4 different curves only from 2 sets of data, which is current and speed, as torque is varied or load is varied. Now, the vertical line here is the rated operating point. We don't typically operate motors for their max output power. Those are usually just a condition, a transient type condition where a motor can deliver more power. But usually at that point, the current will be very high. The current is in the red line, and the motor will start to heat up and eventually damage itself. Motors are primarily damaged by overheating. So typically we back off the rated position to more closely match the maximum efficiency point, which is typically a little to the left of the max power point. So that's a typical motor curve. This one happens to be for a DC motor. So for measuring speed, we have one of 3 methods. 2 of them are optical, and the third is what we call a mechanical generator. This is the mechanical generator. It plugs into the connects to the shaft of the rotating element, and then we read a value off of this tachometer, which is simply a voltmeter. So we get an RPM reading. This unit is not as typical for use because it's analog, meaning you have to figure out the exact value of the RPM. More commonly, we use an optical reflective unit here, or what we call a strobotach. Now, both the strobotach and the optical laser digital tachometer use an optical method, and they use a reflector. Well, this one uses the reflector. The strobotach doesn't need a reflector, but we still use it. So the white dot you see on the shaft, the pulley, will reflect the light from the optical unit. That optical unit receives the reflected signal, and based upon the reflected pulses, which come from the white piece of reflective tape there, then it can determine the RPM. So it's important that you pay attention to where that white spot is, because you need to point the laser tack at it. Now, the strobotach is a timing light. It flashes at a given RPM value, and when that flashes, you'll see that the motor will stand still, or the pulley will stand still, because the light is synchronized with the rotation. So it's a typical mechanically related timing light. Now, we already talked about the torque reading, which is from underneath the electrodynamometer. Speed we now get from our tachometers here. And we're going to use current from this meter. We'll use the special 10 amp rating here. So 10 amps, black is return, and then milliamps or amps, the 10 amp rating, and then we want DC. So make sure the button is out for DC. Over here we'll use the voltmeter. Again, we have volts selected. We're going to be up to 200 volts, over 20 at least, so 200 volt scale. And then again, make sure you are on the DC selection. So now I'm going to power up the unit. It's going to get a little noisy, but I'll do a demonstration on at least the measurements of speed and power. I'm not going to take a torque reading here. This is going to be the no load condition, which of course means no torque. All right, so we'll power up the unit. By the way, always once you have things set up, you simply turn on the power and take readings. No need, and you should not be changing any wiring. All right, so power on, and then we're going to dial up the tachometer, or the motor. So I'm going to set the motor close to its rated voltage, which is listed on the nameplate there of 120 volts. This value doesn't have to be exact. It's just going to be a value we're going to try and keep the voltage to. So we see the voltage at 120.6 volts. The current is very low, so we'll check the value. It's 0.58 amps. So that's the power it takes to run the motor with no load at all. So we'll check the speed. Again, we'll use our laser tack here and we'll position it so that it is flashing on that space where the white tape was. And we see that the reading is pretty stable at around, this says 1365 RPM. Now we'll double check that with the strobo tack. So we'll turn on the strobo tack and immediately you hear the lights flashing. The reading is taken off of this scale here. So we adjust the scale until the timing light will match the speed of the rotating element. And you'll know it right away. Let me get the light over here. You can see the reflective tape there. When the tape is standing still, we know that the flash rate of the strobo tack and the speed of the motor are matched. And of course we go and look at the value, and it is slightly below 1400 RPM. We read over here 1378. Here it looks like it's about 1380. Very close to the value. Alright, so now we have our first data point. Now we are ready to take data with load. So what we're going to do is connect the belt between the motor and the dynamometer to take the first data point. Okay, so we have connected the belt to the dynamometer. I'm not going to connect the AC power, which is the way we load the dynamometer yet, because I want to show you that even without strictly loading the dynamometer, the motor itself or the dynamometer provides a load. So if we look at the reading of the foot-pounds forced inches for torque, we see it's essentially 0. So I'm going to power up the motor, and of course you see a little indication. So that's around 0.7 pounds force inches of torque. The speed, if we check the speed, it will change a little bit. The speed is now at 1354. 1355. The current is 0.77, and the voltage has changed a little bit to 118. Now that is caused because this is now a load. So I'm going to actually adjust the voltage until it is back up to 120 or very close. So there's our voltage, our current minorly changed, and then we can get the reading of the speed and torque. Okay, so the tachometer is 1379 or 80. The torque is, as I said, around 0.6, 0.7 foot-pounds force inches, 0.74 for the current, and 120 for the voltage, 120.2. Alright, so I have applied the AC signal to the dynamometer. This is going to provide a load for the dyno, which then impacts the motor. We connect to the AC supply. The one on the far left, the one in the middle is a variable. So this is 120/208. So this is 120 volts between neutral in the white and the blue. You could use the black, red, black, or blue, but it's just convenient to use the lower version. Alright, so now we're ready to power up. Again, we don't touch any wiring when we're taking data. Alright, so the voltage looks good at 120.4. The current is 0.77, changed a little bit. And the torque is very similar to what it was without the AC supply. When we load it, we're going to turn this dial. As you turn the dial, you will see the unit start to rotate, and that's applying load. So we want to get that first data point. And so again, we get our speed here at 1389. All right, and the torque is still at the 0.6 foot-pound-inches. So now you simply need to adjust the supply until you get the torque reading you want. So I'm going to adjust until I get 1 foot-pound force. And take my speed reading, which is now 1383. My current has changed slightly to 0.80. The voltage is very similar at 120.4. At this stage in the laboratory, or even earlier, you should set up a spreadsheet for data collection. By far the easiest thing you can do to make your lab data and reporting easy is to have a good spreadsheet. So I simply have voltage, current, voltage, torque, current, and speed. I have torque in the second column, so I can plot torque, current, and speed, and the first column will be the independent or x-axis. So here we see the data plotted. Now don't worry that this data looks a little different than what we looked at initially, particularly the speed data going up and down. These values are almost equal to one another, and if I change the scaling to be something closer to what the actual value, which will be 0, you'll see that the curve is fairly straight there for the speed, and the current is going up. So from here, you just need to collect more data, and we'll go up in foot-pounds force one at a time and take the readings. As you load your motor, you will notice you will reach a point, and you can hear the speed of the motor changing. You will reach a point where the dynamometer, which is a spring-based system, becomes unreliable. You can start to hear the noise. You can even see the sparking which is occurring on the motor. And as it starts to rotate, you know you are at the end of your data collection. So just reduce the load, and the unit you are done with your data collection. So all the data collection has been done. A motor speed and current versus torque curves can be plotted directly from the data, and then with calculated values you can get electrical power in, mechanical power out, and then also efficiency. Not quite the ideal that we saw in the data sheets, but certainly close enough to show the principles in action. This motor tops out around 60-some% efficient. Not particularly efficient, but these are not industrial, they're more educational motors. And we end up around 340 some watts out, about a half a horsepower. It's rated at a quarter horsepower. And then the electrical power goes all the way up to almost 600-700 watts. And that's the lab, at least the data collection.